In today's video, we're going to see how we can represent a linear transformation from a vector space V into a vector space W with respect to bases S and T for V and W respectively as a matrix. We will then see how the linear transformation, properties of the linear transformation and properties of this matrix representation are related. Let f from V into W be a linear transformation. Moreover, let the set S be a basis for V and the set T be a basis for W. Then there exists a unique matrix A such that for every vector x and v, the coordinate vector of f of x with respect to t is equal to a times the coordinate vector of x with respect to s. And we're going to see that the jth column of this matrix A is the coordinate vector of f of v of j with respect to t. So to see this, let our coordinate vector of x with respect to s be the vector d1, so on and so forth through dn. Then, if we take a look at the coordinate vector of f of x with respect to t, we're looking at the coordinate vector of f of the linear combination of the vectors in S with the coefficients d1 through dn respectively. So it'll be d1 v1 plus so on and so forth plus dn vn with respect to t. Because f is a linear transformation, we can write it this way. Right? And then using properties of vectors and vector addition, we can write this. But this can be written as this row matrix. I'm sorry, this isn't really a row matrix. This is the matrix whose jth column is f of v sub j, the coordinate vector of that with respect to t, then times the column vector d1, so on and so forth, dn, which is itself the coordinate vector of x with respect to s. So we call this here our matrix A. Of course, that column vector is just our coordinate vector of x with respect to s. Now, we just have to show that this is the only matrix. So let's suppose there's another matrix. So let's suppose there exists a B such that the coordinate vector of f of x with respect to t is equal to b times the coordinate vector of x with respect to s for all x in V. If we go ahead and subtract these two equations, what we get is 0 is equal to a minus b times the coordinate vector of x with respect to s. Right, but this is true for all n vectors. So this is true for every coordinate vector x with respect to s. So what we find is the nullity of a minus b has to equal n. And so the rank has to equal 0. There's only one matrix that has rank of 0. And that's the 0 matrix. So a minus b is the 0 matrix, which means that a has to equal b, which proves that this is the only such matrix. And so the proof is complete. Now the important thing to note out of here is that this matrix is our matrix A. So that is how we find this matrix. And this matrix has a special name. That name is the matrix of the linear transformation. Right, so that matrix that we just found, that matrix A, is called the matrix of the linear transformation F with respect to S and T. Okay, so what we want to do is go ahead and find the matrix of this linear transformation G, which is from P3 to P2, defined as G of A0 plus A1t plus A2t squared plus A3t cubed is equal to A1 plus 2A2t plus 3A3t squared. And we're going to find this matrix with respect to the two matrices, the two bases S and T. Right, so first what we want to do is take the linear transformation of each matrix in S, or each vector in S, and write it as a linear combination of the vectors in T. Right, because remember, our transformation matrix is the matrix whose columns are the coordinate vectors of the linear transformations of those vectors in S. Right, so first we want to look at G of 1 minus t cubed. And recall that 1 minus t cubed is going to be 1 minus 3t plus 3t squared minus t cubed. Well, if you notice, G is just the differential operator. So we're taking the derivative. So we get negative 3 plus 6t minus 3t squared. And we want to write this as alpha 1 times 1 minus t squared plus alpha 2 times 2t times 1 minus t plus alpha 3 times t squared. And let's go ahead and expand all those out. So alpha 1, 1 minus 2t plus t squared, plus alpha 2 times 2t minus 2t squared, plus alpha 3 times t squared. Now our ultimate goal is to find the coordinate vector. Right, so we need to solve for alpha 1, alpha 2, alpha 3. However, we have to do the same thing for 3 other vectors. So for now, let's just hold off on finding the coordinate vector. We'll be able to do that all at once. Right, so now we want to find g of 3t times 1 minus t squared. Right, so that is the same as g of 3t minus 6t squared plus 3t cubed. That will be 3 minus 12t plus 9t squared. Right, we want to write that as a linear combination of the vectors in T. Well, there's no need to reinvent the wheel, right? We already did these expansions. So we get beta 1 times 1 minus 2t plus t squared plus beta 2 times 2t minus 2t squared plus beta 3 times t squared. Right, now we want g of 3t squared times 1 minus t. All right, so that's g of 3t squared minus 3t cubed, which is 6t minus 9t squared. Right, and that is a linear combination of the vectors in T. So gamma 1 times 1 minus 2t plus t squared plus, not v, gamma 2 times 2t minus 2t squared plus gamma 3, I don't know why I did a parenthesis there, times t squared. And finally, we need g of t cubed. That's just 3t squared, and that is delta 1 times 1 minus 2t plus t squared plus delta 2 times 2t minus 2t squared plus delta 3 times t squared. And up here, I don't know why I wrote minus gamma 3. That should have been plus gamma 3 t squared. So let's fix that. And so we now have our 4 transformed vectors from the basis S. Okay. Now remember, we want to solve for each of these coefficients. So to do that, in each case, we're setting up an augmented matrix, right? So our coefficient matrix will be based on these 3 vectors, the vectors in T. And notice for each of the 4, they are exactly the same. So we're going to have the same coefficient matrix for all 4 of these equations, which is why I wanted to wait until the end. So the coefficient matrix, first column will be 1, negative 2, 1. Second column will be 0, 2, negative 2. Third column will be 0, 0, 1. Notice that row 1 represents the constant. Row 2 represents the coefficient of t. Row 3 represents the coefficient of t squared. For the first equation, this will be augmented with the transform, right? So this vector right here, -3, 6, -3. For the second, it'd be augmented with this vector, 3, -12, 9. So why not go ahead and augment again and add 3, -12, 9. Right, the third system, or the third equation, would be augmented with 0, 6, -9. So let's go ahead and add that. And the final equation would have an augment of 0, 0, 3. So let's go ahead and add that. Right, now notice when we go to solve this, this first augment will give us the alpha terms. The second would give us the beta terms. The third would give us the gamma terms, and the fourth would give us the delta terms. So instead of now RREFing 4 separate matrices, we are just RREFing a single matrix. When we go ahead and RREF this, we'll get three by three identity augmented with -3, 0, 0. That'll be augmented with 3, -3, 0. That'll be augmented with 0, 3, -3. And that'll be augmented with 0, 0, 3. Right, so this is I3, right? That's the 3 by 3 identity. This will give us the coordinate vector of G, V1, with respect to t. This one will give us G of V2 with respect to t. Third will give us G of V3 with respect to t. And that fourth one, you guessed it, G of V4 with respect to t. And remember, A is the matrix in which each column is the coordinate vector of the transformation with respect to t. So our transformation matrix, A, is -3, 3, I'm going to do columns, -3, 0, 0, 3, -3, 0, 0, 3, -3, and finally 0, 0, 3. We now look at the relationship between this linear transformation and its matrix. Specifically, the ranks are equal and the nullities are equal. So to prove that the rank of the transformation is equal to the rank of its matrix representation, we use the fact that S spans V and that F is a linear transformation. This allows us to write the range of F is equal to the set of all vectors F of V such that V is a vector in V. Right, well, that means that V is a linear combination of vectors in S. So we can write this as f of C1, V1 plus so on and so forth plus C2, V2. Right? Such that each VI is in S and each CI is a real number. Right? Well, again, F is a linear transformation, so we can write this. And I need to make a quick change I just noticed. This should not be C2V2, this should be CNVN. But this is the very definition of span of f of v1, so on and so forth, f of vn. Right, so in other words, our range is spanned by the transformations of each vector in S. Now, on the other hand, the column space of A is spanned by the coordinate vectors of each transform of S, each vector in S, rather, with respect to T. Right? Now, not only do these two sets of vectors span the respective vector spaces, they're also linearly independent. So these sets are actually bases. We see that they have the same number of elements. So we can conclude that the dimension of the range of F is equal to the dimension of the column space of A. And remember, the dimension of range of F was the rank of F. And the dimension of the column space of A is the rank of A. So the rank of F is equal to the rank of A. Now we have to do the nullities, right? So the kernel of F consists of all vectors V and V for which f of v is 0. But v is in V, so it can be written as a linear combination of the vectors in S. Right, and the fact that F is linear, we can use both of those. Right, so that's the first step, and then we can write this. Right, again, where vi is a vector in S, so each of the vi's are in S, and each of the ci's are real numbers. Since u equals 0 is the only vector such that its coordinate vector with respect to S is equal to 0. The equation that we just wrote is equivalent to this coordinate vector with respect to t is equal to 0. Which means that c1 times the coordinate vector with respect to t of f of v1 plus so on and so forth plus cn times the coordinate vector f of vn with respect to t is equal to 0, which means that a times the coordinate vector of v with respect to s is equal to 0. This allows us to conclude that the dimension of the kernel of f is equal to the dimension of the null space of A. And remember, dimension of the kernel is the nullity. So we have nullity of f is equal to, and the dimension of null space of A is the nullity of A. So we have that the nullity of f is equal to the nullity of A. Right? So let v1, v2, and v3 be finite dimensional vector spaces with bases of s, t, and u respectively. If f from v1 into v2 is a linear transformation, whose matrix with respect to s and t is A, and g from v2 into v3 is a linear transformation, whose matrix with respect to t and u is B, then the matrix of the composite linear transformation h from v1 into v3 defined by h of u equals g of f of u with respect to bases s and u is B times A. All right, well, the matrix of H with respect to the bases S and U is, let's call it C. It is the matrix whose columns are the coordinate vectors of the transformation of the vectors in S under H with respect to T. So it's this matrix. We want to show that the jth column of C equals the jth column of B times A. So to find the jth column of BA, we do the entire matrix B times the jth column of A. Now remember, B is going to be the matrix whose columns are the coordinate vectors with respect to U of the transformation under G of each vector in T. Right, so that's this matrix. And then, of course, our column, our jth column of A will be A1J, so on and so forth, A and J. Sorry about that. Right, but remember these columns, right? This entire column is equal to the coordinate vector with respect to t of the transformation v sub j under f. Right? Now, FVJ is equal to A1J f of V1 plus so on and so forth plus ANJ f of Vj, right? And that comes directly from the fact that we have the coordinate vector. So if we go ahead and let's call this equation 1, right? Therefore, the right-hand side of equation 1 can be expressed as a linear combination of columns of B. All right, specifically what we have is B times the jth column of A can now be written as A1J times this, so on and so forth, plus A and J times G of Wn, its coordinate vector with respect to U, which becomes this which, again, using the fact that G is a linear mapping, we can write this. However, if we look here, let's call this up here number 2. I'm sorry, these should be W's. Oops, that's kind of important. So I need to rewrite this. There we go, that's number 2. This is now f of v sub j. So we now have the coordinate vector of g of f of v sub j with respect to u. But that is the definition of h of v sub j. Well, that itself is the jth column of h. I'm sorry, of C. And so we conclude that C is equal to B times A. Let V and W be finite dimensional vector spaces with bases S and T respectively. Furthermore, let F from V into W be a linear transformation whose matrix with respect to S and T is A. Then, F is invertible if and only if A is invertible, and the matrix of the inverse transformation F inverse with respect to T and S is A inverse. For the first one, recall that F is invertible if and only if F is 1-to-1 and onto. Also, F is 1-to-1 if and only if the nullity of F is equal to 0. But this is true if and only if the nullity of its matrix representation is equal to 0. And this is true if and only if A is invertible. The second statement follows directly from Theorem 3. That concludes today's video on the matrix of a linear transformation. That also happens to conclude our study of linear transformations. In the next video, we will begin our study of eigenvalues. As always, I thank you very much for watching, and I will see you all in the next one.